Hello, this is Chapter 10 Business Analytics Forecasting with Time Series Data. In Chapter 10, the learning objectives are the following. Describe the time series forecasting process. Use smoothing techniques to make forecasts. Use linear regression models to make forecasts. Use nonlinear regression models to make forecasts. Apply cross-validation techniques to model selection. And last but not least, use advanced smoothing methods to make forecasts. Okay, introductory case. Apple Incorporated is an American multinational technology company that designs, develops, and sells consumer electronics, computer software, and online services. On October 29, 2020, Apple announced revenue of $64.7 billion for its fiscal 2020 fourth quarter. The revenue was boosted by stronger than expected sales for smartphones and for telecommuting devices amid a work-from-home trend due to the pandemic. According to CEO Tim Cook, despite the ongoing impacts of COVID-19, Apple is in the midst of our most prolific product introduction period ever, and the early response to all of our new products, led by our first 5G-enabled iPhone lineup, has been tremendously positive. Candace Johnson, a research analyst at a small investment firm, is evaluating Apple's performance by analyzing the firm's revenue. Cadence hopes that Apple's past performance will aid in predicting its future performance. She collects quarterly data on Apple's revenue for the fiscal years 2010 through 2018. Cadence would like to use the information for the below tasks. Number one, explore models that capture the trend and seasonal components of Apple's revenue, and to forecast Apple's revenue for fiscal year 2019. The forecasting process for time series. Observations of any variable recorded over time in sequential order are a time series. Time periods, year, quarter, month, week, day, hour, second, etc. Let Y1, Y2, etc., YT represent a sample of T observations. YT represents the value of time, T. Use big T rather than N to represent the number of observations. A time series is characterized by four components: trend, long-term, up-down movements, seasonal, repetitions over a one-year period, magnitudes of the up-down swings are more predictable, cyclic, wave-like fluctuations or business cycles, durations last several years and differ from cycle to cycle, random, unexplained movements. And here is a graphical representation of the time series, and this would be revenue for Apple and the different time series, as well as the revenue amounts. Qualitative forecasting is based on judgment, prior experience, and expertise. It's attractive when historical data are not available. It's used when future results are suspected to depart from prior periods and cannot be based on historical data. Prone to well-documented bias such as optimism or overconfidence, and it's also difficult to document. Quantitative forecasting is based on historical data and relies on formal models. We will focus on quantitative models, so we need model selection criteria. So numerous models can be used to make a forecast. Each model well suited to capture a particular feature of the time series, and you explore several different models. Model selection is one of the most important steps in the forecasting, and we compare the performance of competing forecasting models. In sample criteria, you have training data set, sample period used for estimation and assessment, and then also does not assess how well an estimated model will forecast or predict an unseen sample. Also, cross-validation. To partition the sample into a training set and a validation set. In the training, we build the model, and the validation is we assess or validate the model, independent assessment of performance, and also utilize out-of-sample criteria. Performance measures are based on the forecast error, using these formulas here. Use multiple performance measures. You can use mean squared error, mean absolute deviation, mean absolute percentage error, and the preferred model will have the lowest MSE, MAD, and MAPE values. MSE heavily penalizes models with large forecast errors and is preferred if relatively large forecast errors are particularly undesirable. The root mean square error is simply the square root of MSE. A large RMSE relative to MAD is indicative of relatively large errors in the forecast. The attraction of MAPE is that it shows the error as a percentage of the actual value, giving a sense of the magnitude of the errors. Simple smoothing techniques. Any data collected over time are likely to exhibit some form of random variation. These methods are for when the time series is particularly described by random variation around an unknown level. There are no variations due to trend and/or seasonality. A simple plot of the time series provides insights into its components. A jagged appearance caused by abrupt changes in the series indicates random variations. Smoothing techniques are employed to reduce the effect of random fluctuations. It can also be used to provide forecasts if short-term fluctuations represent random departures from the structure with no patterns. Attractive when forecasts of multiple variables need to be updated frequently or it is not practical to develop complex forecasting models. We will consider two smoothing techniques here, moving average technique and exponential smoothing technique. The moving average technique is simple and popular. The average of the most recent M observations, where M is a fixed integer. So the moving average equals the sum of the most recent M observations divided by M. The term moving is used because as a new observation becomes available, the average is updated by including the newest observation and dropping the oldest observation. Makes sense, right? Example. In preparation for staffing during the upcoming summer months, an online retailer reviews the number of customer service calls received over the past 3 weeks, or 21 days. And we can see from the chart we have the days here and then the number of calls. Construct 3-period moving averages, plot the time series and the moving averages, and use the 3-period moving average to forecast. Calculate MSE, MAD, and MAPE or MAPE. Example continued. So here's the formula. We plug in all the information, and this is what we get, 295. Here's the plot, the number of customer service calls, and our predictive measures. And we chart this out, and we use these formulas here. The moving average technique has shortcomings. The choice of M is arbitrary, and choose M to minimize MSE, MAD, or MAPE, and all M observations have the same weight. It may not be appropriate to give equal weight to all recent observations. The simple exponential smoothing technique assigns exponentially decreasing weights as the observations get older. And here's the formula for that. The forecast equation simplifies to this, is usually taken to be y sub 1, and the choice of initial value is less important if the number of observations is large. The optimal choice is determined by trial and error. Evaluate various values and choose the one that has the smallest MSE, MAD, MAP, or other criteria, so choose. So let's revisit the example. These are the days and the calls. Construct the simple exponentially smooth series. Plot the time series, use the smooth series to forecast and calculate the acronyms and choose delta. Compare the value of those obtained using the moving average technique. So example, y sub 1 equals 309, y sub 2 equals 305.60, and y sub 3 equals 301.28. What does all this mean? And here's the plot. And it's exponentially smooth here, where we had the spike and the peak. I'm going to skip this one. So let's take a look at linear regression models for trend and seasonality. The smoothing techniques are used when the time series has no trend or seasonal fluctuations. The linear trend model is used to extract long-term upward or downward movements of the time series. The linear trend model is a linear regression model that uses time as the predictor. Appropriate when the time series does not exhibit seasonal variations or has been stripped of its seasonal variation, also known as being deseasonalized, which is smoothing. How about linear regression models for trend and seasonality? Example, a local organic food store carries several food products for health-conscious consumers. The store has witnessed a steady growth in the sale of chef-designed meals, which are especially popular with college-educated millennials. For planning purposes, the manager of the store would like to extract useful information from the weekly sales of chef-designed meals for the past year. Visually inspect the time series to confirm the existence of a trend, estimate and interpret the linear trend model for the sales, and forecast the sales for the next 4 weeks. So we take a look, and we look at the sales and the week, and then we plot our line here. Every week, sales increased by about $96.84. 75.38% of the sample variation in sales are explained by the sample trend line. Week equals 53 to forecast sales for the next week. The sales, 7,130.66. Week 54, 55, and 6 to forecast sales for the subsequent 3 weeks as these numbers here. With seasonal data, we estimate a trend regression model that also includes dummy variables to capture the seasonal variation. Use dummy variables to describe seasons. With quarterly data, a linear trend model with seasonal dummy variables is this formula here. And D sub 1, D sub 2, and D sub 3 are the dummy variables representing the first 3 quarters. T is the predictor variable corresponding to the consecutive time period. And here's the forecast. Forecast based on the estimated model. With Amazon.com at the lead, e-commerce retail sales have increased substantially over the last decade. And this is linear regression models for trend and seasonality continue. Consider quarterly data on e-commerce sales in the United States from 2010 to 2019. And these are e-commerce retail sales. Visually inspect the data to confirm the existence of a trend and seasonality. Estimate and interpret the linear trend model with seasonal dummy variables for e-commerce retail sales. And forecast e-commerce retail sales for the last 3 quarters of 2019. And here's an example of the plotting of it. Do we see a trend? Here's the example, and these are the dummy variables and the time series. Here are the sales. Relative to the 4th quarter, e-commerce sales are about $22,000 lower in the other 3 quarters. The predicted quarterly sales increase by about $2,650 million every quarter. Here's the formula we used. And this is for R, I think. Yeah. Okay, so we have discussed non-causal or purely time series models that capture trend and seasonality for making forecasts. They do not offer any explanation of the mechanism generating the target variable and simply provide a method for projecting historical data. Causal models, on the other hand, are standard regression models that exploit the relationship between the target and the predictor variables for making forecasts. Example, we can use causal models to forecast the sale of a product using predictive variables such as the firm's advertising budget and its pricing strategy. The regression framework also allows us the flexibility to combine causal with time series effects. This is non-linear regression models for trend and seasonality. A linear trend model implies that for each period, the value of the series is expected to change by a fixed amount. The exponential trend model is attractive when the expected increase in the series gets larger and larger over time. In essence, there is exponential growth. The model is specified as this formula here, and the estimated model is used to make the forecast as follows. According to data compiled by the World Bank, the world population has increased from 3.03 billion in 1960 to 7.53 billion in 2017. This rapid increase concerns environmentalists who believe that our natural resources may not be able to support the ever-increasing population. Additionally, most of the rapid population growth has been in 34 low-income countries, many of which are located in Africa. Consider the population data in millions for low-income countries from 1960 to 2017. Here is the chart. Estimate and interpret the linear and the exponential trend models. Use MSE, MAD, and MAPE to select the appropriate model. Forecast the population in low-income countries for the following year, which would be 2018. Linear trend model, here's the formula here. The population grows by 9.6799 million each year on average. And the exponential trend model, the population grows by 2.64% each year on average. Here's the chart of the trend. Example, so for 2018, T times 59, and the forecasted value is here, and it would be 748.5195 million. This is with R. Use a quadratic trend model when the relationship is captured by a U-shape or an inverted U-shape. A beta sub 2 determines the direction, either U-shaped or inverted U-shape. A polynomial trend model of the order Q. Do not use MSE, MAD, and MAP to compare polynomial trend models. The values decrease as the order increases. Use adjusted R-squared to compare polynomial trend models. We can also add dummy variables for seasonality to these non-linear model options. And here we go with that. Your dummy variables in the different quarters, plug that all in. The objective outlined in the introductory case is to use Apple's quarterly revenue in millions of dollars from 2010 to 2020. Estimate the linear and the quadratic trend models with seasonal dummy variables for Apple's revenue. Determine the preferred model and use it to forecast Apple's revenue for fiscal 2021. Here's our charts and our subs that we put in. Here's the example continued, the linear trend, the quadratic model, and the forecast based on the quadratic trend model. Data partitioning and model selection. So far, we have assessed the competing forecasting models on the basis of in-sample criteria. The predictability of a model is assessed in the same period used to build the model. This does not help gauge how well an estimated model will predict an unseen sample. Apply cross-validation techniques using the holdout method. Do not randomly partition the data into training and validation. This breaks the time series structure and creates holes. Sequential partitioning into earlier and later periods. Training, early period, build estimate model. Validation, later period, assess model with out-of-sample criteria and based on the forecast error formula is the forecasted value, and then compute MSE, MAD, and MAPE to determine the preferred model. Use the entire data set to re-estimate the preferred model. Example, revisit Apple's quarterly revenue data in millions of dollars from 2010 to 2020. This data set was outlined in the introductory case. Let the training and the validation sets comprise the periods from 2010 to 2018 and 2019 to 2020 respectively. Use the training set to estimate the linear and the quadratic trend models with seasonal dummy variables and compute the resulting MSE, MAD, and MAP for the validation set. Determine the preferred model and re-estimate it with the entire data set to forecast Apple's revenue for fiscal year 2021. Example, estimated trends with the training set here. Here's where we plug in our chart and re-estimate the quadratic model with the entire data. The quarterly revenue forecasts for fiscal year 2021 are 81.964 million, 63.398 million, 57.489 million, and 60.663 million. And here's the example for R. Advanced exponential smoothing methods. The Holt exponential smoothing method incorporates long-term upward or downward movements. This is appropriate when the time series does not exhibit seasonal variations or has been deseasonalized. The forecasts depend on the values of the smoothing parameters. The parameter values can be user-supplied, computer-generated by minimizing MSE or some other performance measure. Computer-generated values are prone to overfitting, where the selected model does well in the sample period, but not so well into the future. Example: revisit the population data in millions for low-income countries from 1960 to 2017. Let the training and the validation sets comprise the periods from 1960 to 2000 and 2001 to 2017, respectively. Use the training set to implement the Holt exponential smoothing model with user-supplied parameters, as well as computer-generated smoothing parameters, and compute the resulting MSE, MAD, and MAP for the validation set. Determine the preferred model and re-implement it with the entire data set to forecast the population in low-income countries for 2018. Here's the example with Excel. And here's the example with R. This is the example continued with R. We look at the chart here and see the formula. The Holt-Winters exponential smoothing method incorporates trend and seasonality. It's also called the triple exponential smoothing. It uses three recursive equations to smooth the series for level, trend, and seasonality. There are two structures: additive, the seasonal variations are roughly constant over time, and multiplicative, the seasonal variations are proportional to the level of the series. Example: revisit Apple's quarterly revenue data in millions of dollars from 2010 to 2020. Let the training and the validation sets comprise the periods from 2010 to 2018 and 2019 to 2020. Use the training set to implement the Holt-Winters smoothing method with additive and multiplicative seasonality and compute the resulting MSE, MAD, and MAPE for the validation set. Determine the preferred model and re-implement it with the entire data set to forecast Apple's revenue for fiscal year 2021. And this example is continued with Excel. And then the last one with R. And the last one continued. Thank you for listening.